Welcome back. You're probably thinking that at the end of Module 8 I promised there was only one more module left. Well, they slipped another module in on you, as you know by now. But you can be happy because you probably know a lot more about geodatabases and data management than you used to know. So this is the last module, at least as far as I'm concerned, in this course. So we're going to talk about remote sensing and GPS. The last module for you was geodatabases and data management, and hopefully you learned a lot there and you'll be able to use that in the future. Okay, remote sensing is a very big topic, and in the number of short videos I'm going to do here I won't really do it much justice. If you're interested in this, or if you need to do things involving remotely sensed data in the future, you might think about this certificate in GIS, the program we have in the geography department, because there are 3 different courses in the certificate program that involve remote sensing. There are some advanced topics you can look at. There's a course that's hydrologically focused, and then there's the basic remote sensing GIS integration course, which goes into a lot more depth on what I'm going to talk about in these following videos. So what the heck is remote sensing? It's measurement or acquisition of some property of an object by a recording device that's not touching the object. So it's measuring something without touching it. It's been going on for a long time. This is an example from, it looks to me like probably the 30s or 40s. I'm not quite sure what that instrument is, but I'm guessing that that might be something that was called an optical pyrometer, and by looking through an optical pyrometer you could match colors with what it was aimed at, and when the colors were matched you would be able to determine what the temperature of the thing you were looking at was. So you know how things get red hot and white hot and things like that. Well, based upon the color that you see in your pyrometer you're able to calibrate the temperature, and it would be a way to measure really hot things without trying to touch them, which is valuable. There are a whole bunch of different systems that you can use to remotely sense data, and those systems are going to be important in a lot of different application areas. You can see there's a table here that has a whole bunch of application areas, and it has a whole bunch of different types of remote sensing systems that you can use. And what you'll find is most of the time these remote sensing systems are classified according to what portion of the spectrum they're sensing, and I'll talk more about that in a couple slides. Okay, so like everything else, we classify things, we break them into types. So for remote sensing systems we break them into 2 basic types. There's passive systems, and what passive systems do is they're detecting energy generated by the sun that's reflected off of something. So what you do is you detect what bounces off of the thing you're looking at, and it's bounced off or reflected energy from the sun. Active systems don't use the energy from the sun, but they produce their own signal, and they detect the energy that bounces off of an object that's part of what the signal was that was actively generated. From the table before, we have these useful remote sensing systems, which was the header for the columns on that table. The ones on the left side of that table are all passive systems, and the ones on the right side of the table are all active systems. Okay, this is all based upon energy spectrums, and back in physical science, way back, you probably learned about waves and how especially the sun can be thought of as waves of energy and particles of energy, and there's that whole quantum mechanics thing. But when you think about waves, you can talk about 2 basic properties of a wave, and those are the frequency of that wave and the wavelength of the wave. And so the frequency is the number of waves that fit inside of a unit time window. The wavelength is the distance between peaks in a wave, between adjacent peaks. So you know that the frequency is the inverse of the wavelength, and you can think about things in terms of what the frequency is or what the wavelength is. When you think about short frequencies or high frequency things, it takes more energy to maintain those things. So shorter frequencies, higher frequencies, are more energy than lower frequencies. Okay, longer wavelengths. Shorter wavelengths, more energy. Longer wavelengths, less energy. What can waves do? Well, waves can bounce. That's one thing you you'll remember. Waves can bounce off of things. They can be absorbed by things. Waves can hit things and scatter in all different directions, and they can do what's called diffracting, which is move in a programmed set of directions from an obstruction. And so you've got absorption, reflection, scattering, diffraction. These waves can do a lot of things. So here we have the electromagnetic spectrum, and the way this is drawn here, we have wavelengths that are long wavelengths on the left side, wavelengths that are short wavelengths on the right side. So these short wavelengths are higher frequencies. The longer wavelengths are lower frequencies. Okay. Generally, when we're talking about the electromagnetic spectrum of the sun, we talk about things and we show charts of things that show things by wavelength and not by frequency. So what we're going to do is we're going to flip this around so that when we think about what the sun is emitting, we think about short wavelengths being on the left side of the charts. Short wavelengths, high frequency, those are high energy things. And the long wavelengths are out at the right hand side of the graphs, and those are going to be lower energy, lower frequency. So what does the sun do? The sun puts out a spectrum of energy, and the amount of energy that the sun generates depends upon the wavelength of the energy. So at very short wavelengths, it's not putting out a lot of energy, and then it picks up right away and it starts to put out a lot of energy, and the amount of energy that the sun puts out peaks in this area right here, and then it begins to tail off as the wavelengths get longer. The amount of energy that it puts out gets to be less and less. So amazingly, our eyes have evolved to the point of sensing areas up here where the sun's energy is the highest. So we're able to see this portion of the sun's spectrum. All of the rest of the sun's energy, we can't see it with our eyes. It's out there, but we can't see it. So we can't see X-rays and gamma rays, but they're out there. We can't see thermal infraration and radiation and things like that, but it's out there. Can't see radar waves, but they're out there. Okay, so the sun puts out this energy, but it doesn't all make it down to the surface of the planet, and that's because the atmosphere absorbs the waves as they're coming in, and so depending again upon the wavelength of the energy, the atmosphere will absorb or not absorb. So the dark areas in this chart are the areas that the atmosphere is absorbing. And again, you can see in the visible, the atmosphere doesn't absorb as many things. And in some other wavelengths, excuse me, I have to close the window. Sorry for that interruption. That was a weed eater outside the window. Okay, so we have these energy pathways. We've got the sun out here putting out that nice smooth energy curve. And things from the sun can hit the atmosphere and be absorbed by the atmosphere. And when the atmosphere absorbs things, it can re-emit the energy that it absorbs from the sun. But when it re-emits the energy, it's going to emit it at a longer wavelength than the wavelength that was absorbed. The sun can go to the ground and the surface can absorb it and get warm, and when the surface gets warm, it's going to re-emit thermal radiation, which is a longer wavelength. So absorption results in re-emission, but at a longer wavelength. Things can get reflected from the clouds, so they can just bounce right off the clouds and they don't even hit the surface. They can also bounce off the surface, and that's going to be one of the main things that we're going to be able to sense is the energy comes in from the sun, bounces off what it is we're interested in, and gets to our remote sensor, and we're able to store information about what was reflected. So if we know what's going on with the sun, and we know where the sun is at and our sensor are at with respect to the surface that we're looking at, we're going to be able to determine what type of material that surface was by what it reflected. Sun can also be scattered in the atmosphere, and so some of that ray that would have otherwise gone past what we're looking for might have gotten scattered and knocked into the sensor. When things reflect, this atmosphere can again scatter things, and when it scatters things, it might scatter things to the sensor. So you can imagine that when you have a sensor that's sensing energy from someplace, it's getting energy inputs from lots of different places, and depending upon the geometry of what's going on with the sun and the surface and your sensor, it's going to be kind of complicated to get an actual number for what you're seeing in terms of the energy that's reflected. So there's a bunch of complicated remote sensing electronics that can be put into drones or helicopters or a little bit higher up in jet planes or all the way up into satellites. So we have these transducers, these remote sensors that are located on things above the ground that can watch a certain area of the ground, and when the sun's energy hits that area and reflects back up to the sensor, they're able to determine what type of materials there are that that thing is reflecting off of. And again, you see some acronyms. This is the instantaneous field of view, which is how much of the surface that sensor is seeing. You've got these things called above ground level altitudes, so you can imagine the higher you get, the smaller the field of view you're going to have, and that's all going to come out in resolution, which I'll talk about in the next video. So how does it work? Well, there's a bunch of electronics in these sensors, and the electronics are sensitive to certain wavelengths of light. So in this example, what happens is, if wavelengths of light in these wavelength bands, let's say 500 to 700 nanometers, hit the sensor, it's going to produce a voltage output. And so depending upon how much energy of these wavelengths hits this sensor, the voltage will go up or down. So this piece of the sensor is specifically tuned to sense this piece of the spectrum. Okay? Different pieces of the sensor can be customized with different type of electronics to sense different portions of the spectrum, and that's how we get the information that we need to determine what it is we're looking at. So how do we store all this data? Well, you can imagine different sensors that are sensitive to different bands of wavelengths in the spectrum. And so in this case, when we look at things like images, usually we have a red sensor, a green sensor, and a blue sensor. So we have sensors that are sensitive to the bands that are the visible bands that look blue to us, look green, and look red. When we put those together, we're going to be able to get a color image. Okay? So what the sensor does is it senses energy in a certain wavelength, and it stores it in a separate raster data set for that raster band, or for that energy band. Generally, they store these things in what is called 8-bit data storage. Sometimes there's more high-resolution data storage, but 8-bit can store anything from 0 to 255. So what you end up getting is what's called a brightness value. And the brightness value is telling you basically how much energy is being received by the sensor in the band that you're interested in. So the blue band here is getting brightness values of 15 on a scale of 0 to 255. And so when you draw this or display this in a sensor, you're going to give this pixel 15 255ths of the amount of total energy that you'll need for your visible image. There's a whole bunch of different hardware that's associated with these sensors, different ways to collect the information. With the exception of this first one, these other ones are all digital. So they have electronics that's sensitive to different wavelength bands in the spectrum. Things bounce off the surface, and through things like lenses, the energy is impinged upon the sensor, which has the electronics in it, and that will send a voltage out, and the storage occurs, and all the complicated things trying to figure out what all that means. This one in the upper left is the analog version. This is like a film camera. And instead of having digital electronics and digital storage, what happens here is there are these silver halide crystals that are sensitive to different bands of the spectrum, different portions of the spectrum. And so the film basically burns in place the amount of energy that comes from the different types of pieces of the spectrum. Okay, so when the sun gets through all of these problems of being scattered or being absorbed or whatever, and it hits the ground, it bounces off, it gets to the sensor. When it hits the ground, different materials will reflect different wavelengths of energy. So different materials might absorb part of the spectrum, and they might reflect part of the spectrum. And what this shows is the reflectance, or the percentage of what hits the material that bounces off, of different types of materials. So you can see that water has a fairly uniform reflectance and kind of a low reflectance, so it doesn't really matter what wavelength hits the water, it's going to reflect it fairly uniformly. Conifers, vegetation, absorbs a lot of energy at these lower wavelengths, and it reflects a lot of energy at these wavelengths. So you can imagine if you have a sensor that's sensitive to this portion of the spectrum, it's going to be able to see things that we can't see because this is outside the visible portion of the spectrum. It's going to be able to see things like vegetation. And vegetation is going to look different than soil. So depending upon the material and the atomic makeup of the material, it's going to reflect different portions of the spectrum. If we have sensors that are sensitive to those portions of the spectrum that a material reflects, we're going to be able to say, I know what kind of material that is. One of the most popular things to use the remote sensing information for is to look for vegetation. And the most commonly used index or measure of vegetation is called Normalized Difference Vegetation Index. And that's based upon the fact that chlorophyll in actively growing vegetation absorbs energy in the red visible portion of the spectrum. So it takes that energy and it uses it to do photosynthesis. But plant materials don't want to absorb all of the energy from the sun because they'd get too hot. And if they got too hot, they would use too much water and they wouldn't be able to outcompete other plant materials that didn't need as much water. So they've evolved to reflect in the near infrared. And that's the portion of the spectrum that's kind of adjacent to the visible portion of the spectrum on the right-hand side or the longer wavelength side. So when you look at this, you see reflectance of vegetation. This is the visible portion of the spectrum. It's absorbing a lot of the energy in the visible portion of the spectrum. It reflects a little bit more in the green than in the red and the blue, and that's why vegetation looks green to the eye, because it's reflecting that green portion of the spectrum. But when you get out here past what we can see, you see that in the near infrared, vegetation is highly reflective. So that energy will bounce off the vegetation and get to our remote sensor, and we're going to be able to sense vegetation. Different materials reflect different things. Here again we have water showing this as kind of a low reflectance, fairly uniform. We have vegetation reflecting in the green, absorbing in the red and the blue, in the blue and the red, and then high reflectance in this near infrared. Dry soil is a little bit different, so depending upon the amounts of energy we get in different bands, we're going to be able to look at the ground and say, that looks more like dry soil than it does like vegetation. And that's how we do land cover for remotely sensed data. And this is a graphic that basically shows that. It says I'm going to reflect that near infrared, so that's going to bounce right off of me. I'm going to reflect some of the green, or more of the green than the red and the blue. That's why it's going to look green to our eyes. And I'm going to absorb the red and the blue, and that's what I'm going to use to drive my photosynthesis. How do we calculate this index? Well, it's a normalized index, which means we're going to divide it by something, so that it depends upon not the absolute magnitude of the energy, but the proportion of the energy. We're going to take how much is reflected in the infrared range, and we're going to subtract how much is reflected in the red range. We're going to divide it by the total reflected in the infrared plus the total in the red. So you can imagine if everything were infrared, we would have infrared minus 0 over infrared plus 0, and we would have an NDVI of 1. If everything were red and there weren't any infrared, so there wasn't any vegetation bouncing off, reflecting, we would have everything in the red would be negative, everything in the red would be positive, we'd have minus 1. So the vegetation index is going to range from minus 1 to plus 1 being completely and totally vegetation, minus 1 being not vegetation at all. And here's an example of a map that you might draw under one of those strange projections from way back in module 2 or 3 that shows the normalized difference vegetation index of the land masses in the planet. And so it shows this is green, which is going to have a high NDVI, and you can see these portions of the planet that aren't near those deserty zones are greener. Wetter places are greener. Places away from the desert zones, the 30-degree plus minus latitudes, are going to be more deserty. And so this is a really good index that's used when you do land cover data to look for vegetation. a whole bunch of things reflect a whole bunch of different areas of the spectrum. So if you have sensors that are sensitive to small portions of the spectrum, you're going to be able to see things like areas in here that reflect a lot, or areas in here that reflect a lot. But each one of these is going to require an individual sensor, and so this is what the visible sensors are going to give us. This is what imagery is: blue, green, and red. A lot of imagery these days includes near-infrared bands, so there's a sensor that can sense that. So sometimes nowadays we can get visible plus this, which allows us to look for vegetation. There are systems which are called hyperspectral or multispectral that are going to have more sensors along the spectrum and be able to see more things. As a last example, sometimes we think of everything as coming from the sun, and in this example the yellow is that curve that the sun is putting out, and these other curves are curves that lights, human-made lights, put out. And so the purple curve is an incandescent light, and you can see that the purple curve most closely resembles that of the sun. So an incandescent light is going to most closely resemble light from the sun. And then there's some other curves in here. We have the blue, which is an LED, and so you can imagine that because these lights put out different spectra, when this light bounces off something and you see it, then you're going to see basically different colors or different types of light depending upon what the source of the light is. So an LED is going to look different than a compact fluorescent, which is going to look different from an incandescent. So they're all going to look different from natural light from the sun. And so that's why when you look in the sunlight, things look different than when you look indoors, and if you're under a fluorescent light, it looks different than when you're under a CFL or when you're under an LED. So that's kind of where that all works out in remote sensing spectrum. Okay, so that's plenty of introductory information on remote sensing. Next time I need to talk about resolution, because there's a lot of factors that come into the resolution of the data that you're going to get from your remote sensors, and depending upon the resolution of the data, you may or may not be able to ask questions of the data that will help you answer the questions that you really have about real-world properties of real-world phenomena. So next time I'll talk about data resolution. See you then.